Okay, let's dive right into this explainer and systematically break down the massive cultural trend of cold plunging to see what the science actually has to say. I mean, you see it literally everywhere right now, right? You've got athletes in ice baths, influencers raving about their cold showers, and high-end wellness clinics charging a premium for specialized cryotherapy sessions. But we really need to separate the biological facts from the social media fiction here. So we're going to look closely at a comprehensive review on cold exposure and metabolic health to understand exactly what is happening inside your body when that temperature drops.
And really, the big question driving all of this curiosity is simply this. Can freezing yourself actually burn fat? Are these icy therapies a legitimate cellular level metabolic miracle, or are they just exaggerated hype driven by a massive rush of adrenaline and the placebo effect? To answer that, we've got to look way past the shivering and the initial shock of the cold water and zoom way, way down into a very specific type of tissue that researchers are absolutely obsessed with right now.
Section 1. Meet your brown fat, the metabolic furnace.
So, to understand cold-induced metabolism, we first need to meet the biological star of the show. That's brown adipose tissue, or BAT for short. And this perfectly highlights the difference between the two main types of fat in your body. See, most of the fat we typically think about is white adipose tissue, or WAT. Think of white fat kind of like a woodpile sitting in your backyard. It's just a passive storage site for excess energy. But classical brown adipose tissue, it acts entirely differently. It is not a woodpile, it's a furnace. Brown fat actively burns fuel to create heat, which is a process absolutely vital for maintaining our core body temperature when we're exposed to the cold.
Now, the crucial point is how your body actually generates that heat. When you first step out into a freezing environment, your body relies on what's called shivering thermogenesis. This is entirely muscle-based. Your muscles rapidly contract and relax to generate heat. We've all been there, right? You're freezing, your teeth are chattering. But through long-term cold adaptation, your body actually shifts the workload. It moves away from all that muscle shivering and fires up non-shivering thermogenesis. And this is exactly where your brown fat furnace turns on, seamlessly burning energy to keep you warm without the need for your muscles to violently spasm.
When you look at the mitochondrial pathways for BAT thermogenesis, you are essentially looking at the literal engine room of this furnace. Pay attention to the specific fuels being tossed into the cellular fire here. We're talking glucose, fatty acids, and amino acids. During cold exposure, your brown fat acts like a giant metabolic vacuum, pulling these circulating metabolites right out of your bloodstream. They enter the TCA cycle, that's the tricarboxylic acid cycle, and ultimately ignite what is known as the UCP1 pathway, or uncoupling protein 1. This is a very specific biological switch that literally uncouples or diverts your energy production to just release pure, unadulterated heat. It is an incredibly demanding metabolic process.
Section 2. Rewiring Metabolism. Human clinical data.
Okay, so what does this complex cellular mechanism actually do to a real human being just sitting in the cold? Well, the clinical data on mild cold exposure is pretty fascinating. Studies show that sitting in just 17 degrees Celsius air, which is roughly 62 degrees Fahrenheit, so we're talking a mild cold without shivering, for 2 hours can improve your insulin sensitivity by about 20%. That is a major metabolic shift. On top of that, researchers have documented increased levels of HDL, the good cholesterol, alongside massive boosts in healthy signaling lipids. Specifically, one trial found that omega-6 oxylipins increased by 47% and omega-3 oxylipins shot up by 77%. These changes directly correlate with a significantly healthier cardiometabolic profile. We also get to see the incredible power of human adaptation. Get this, a 4-week human study where subjects were exposed to mild cold for 2 hours every single day showed that the oxidative capacity of their brown fat increased by an impressive 2.6-fold, meaning their biological furnaces literally grew stronger and way more efficient at burning fuel over the course of just 1 month.
But we do have to look at the full picture here to be objective. While these numbers are super exciting, adult humans actually have very little brown fat, especially when you compare us to infants, who rely heavily on it just to survive and stay warm. In adults, BAT is mostly just found in these tiny little deposits around the neck and the collarbone. Because of this extremely small volume, scientists highly debate if BAT alone is truly driving all those massive metabolic improvements we just talked about. In fact, some of those positive lipid changes we saw showed only a very weak correlation to actual BAT volume. That suggests there are other complex non-BAT mechanisms totally at work in the human body during cold exposure.
Section 3. Mice versus human reality, the clinical divide. To really understand this gap in the research, we need to look at how your body even knows it's cold in the first place. Meet TRPM8 and TRPA1. You can think of these as microscopic biological thermometers located right inside your sensory neurons. TRPM8 is highly sensitive to non-noxious, mild cold temperatures. TRPA1, on the other hand, acts as a nociceptive receptor, which just means it detects painful, noxious cold, usually stuff below 18 degrees Celsius. When the temperature drops, these channels snap open, calcium rushes in, and bioelectrical signals get sent straight down into your nervous system to kickstart that thermogenesis we talked about.
Now, here is where we see a massive contrast in the research. In mice, researchers can trigger these microscopic thermometers without even using cold temperatures. By feeding mice specific compounds like menthol or insulin, which chemically activate that TRPM8 sensor, researchers can practically cure obesity and glucose intolerance in the rodents. I mean, the mice are literally burning fat just by eating menthol. But the second we look at humans, the clinical data completely falls off a cliff. There is absolutely zero human clinical data proving this chemical activation works for us. The research on human cold receptors is overwhelmingly scarce, and right now it's pretty much entirely limited to test tube studies.
So you might be wondering, why don't we have a standardized medical cold treatment yet? Well, the clinical translation is heavily hindered by a few major hurdles. Right now, human studies suffer from completely unstandardized protocols. One study will use a freezing ice bath for 10 minutes, another uses a 62-degree room for 2 hours, and yet another uses a high-tech water-perfused cooling suit. Add to that the issue of flawed or just wildly inconsistent cooling equipment, plus our incomplete understanding of human brown fat in general, and it becomes incredibly difficult for scientists to confidently prescribe cold exposure as a reliable everyday medical therapy.
Section 4. The future of cold. Risks versus rewards.
So bottom line, is cold therapy safe? And is it ready for the mainstream as a real treatment for obesity or diabetes? Well, the crucial point you have to remember is that cold exposure is not just some harmless spa treatment. It is an extreme physiological stressor. It triggers massive sympathetic nervous system activity. We're talking huge adrenaline and norepinephrine spikes, which leads to immediate vasoconstriction and very real cardiovascular stress. Now, for young, healthy athletes, this might be totally fine, but researchers strongly warn that these cardiovascular risks are highly dangerous for vulnerable populations, specifically older adults or anyone who already has pre-existing conditions like cardiovascular disease or advanced metabolic disorders.
The researchers actually put it perfectly in their review, stating further research is necessary to elucidate these risks and develop strategies balancing the benefits and harms of cold exposure for clinical translation. We simply cannot ignore the very real physiological harms just in the pursuit of activating a few ounces of brown fat. The dosage, the method, and the patient's individual health profile all have to be perfectly balanced.
Which leaves us with this final question for you to consider today. Are the potential metabolic benefits truly worth the icy plunge? Look, there is undeniable, fascinating cellular science showing that cold exposure can increase insulin sensitivity, boost healthy lipids, and ignite the UCP1 pathway in our brown fat. That's real. But there is also a vast, vast gap between curing obesity in mice and safely treating human beings. So before you step into your next cold shower or jump into an ice bath, I challenge you to weigh this incredible biology against the viral hype. Understand the stress you are putting on your heart. Know the limitations of the current clinical data, and ask yourself, is your body truly ready for the chill?